Check. 1, 2, 3, 4. Okay, good.
Okay, there it's up. They still have a few minutes.
Good morning, everyone. Welcome to our 8 a.m. press conference. This one is on new observations of Europa from the Hubble Space Telescope. We have 4 speakers who will speak in this order. James Green with NASA's Planetary Sciences Division in Washington, D.C. Lorenz Roth with the Southwest Research Institute in San Antonio, Texas. Joachim Saur with the Institute of Geophysics and Meteorology at the University of Cologne in Germany, and Kurt D. Retherford with the Southwest Research Institute in San Antonio.
May I have the first slide, please? Europa is a moon of Jupiter, and it was discovered by Galileo in 1610 with his new telescope. This beautiful moon is slightly smaller than our own moon, so it is a fairly substantial object. It is in an elliptical orbit about Jupiter with about a 3.5-day period. And during that time, it gets huge tugs and pulls, not only from Jupiter, but also from the Galilean moons. Now, the image shown here of Europa was taken by NASA's Galileo spacecraft, which orbited Jupiter from 1995 to about 2003. Now, the Galileo spacecraft made only 11 close flybys of Europa, but it provided us a fabulous glimpse of this very special object. And here are just some of the important discoveries. As you can see, the surface of Europa has extensive cracks, showing the tidal stresses that it has experienced over time. It has very few craters, and this implies that the moon has resurfaced itself perhaps within the last 50 million years, even though this object is billions of years old. Now, a vast ocean exists underneath this icy crust with more liquid water than there is here on Earth. Now, the presence of the tidal heating and the vast water resources has really led a lot of our scientists to speculate that the Europa that we know today may harbor life. This has made it a top destination for future planetary missions. Now, there are several models as to how thick the crust is, this icy crust on Europa, but these models have restricted the ability of the ocean to communicate with the surface. Now, the observations that we present today will provide significant excitement in the scientific community, as we are now forced to refine or create new models of Europa. I am sure that the data will change our understanding as to how Europa has evolved over time. Now I would like to turn over the presentation to Lorenz to talk about the fabulous results from Hubble. Lorenz?
The images you see here are ultraviolet images taken by the Hubble Space Telescope in December last year, and in these images we were able to detect water vapor at Europa's south pole for the first time. To the left you see an image that is showing only emission coming from hydrogen. To the right you see an image that is showing emission only coming from oxygen. And Europa's position here is indicated by the white circle, so there's Europa in the image. And the emission in this highlighted in red circle at the south pole of Europa kind of led us to this conclusion. And the similar shape of these signals and the relative brightness of the hydrogen emission in comparison to the oxygen emission points to the existence of plumes of water vapor about 200 kilometers high at the south pole or near the south pole of Europa. Next slide. We have 2 more observations of the same kind. These were taken in October 1999 and in November last year. And in these images, here we see the hydrogen image. We do not see any signals from plumes like we do see in the December observations from last year. We looked then at the position of Europa in its orbit around Jupiter and found that Europa is actually at pericenter or near pericenter. That means it's close to Jupiter during the observations from October 1999 and in November 2012, whereas Europa is far away from Jupiter, close to epicenter, during the observations from December last year. And the bottom panel shows a view of Europa's south polar region, or plots of Europa's south polar region. So you look from below the moon directly onto the South Pole. And the dots here show in a digitized way the fractures, these cracks you see all over Europa's surface. And in the first two images or plots to the left, you see these circles are all white, which means there's no tension exerted on these fractures. But during the December observations, you see, like highlighted in red again, there are like large fractures that experience tension during this observation, and this tension might open the fractures and allows the water vapor to escape and form these plumes there. So that's what we found in the latest observations, and I'm going to hand over to Joachim now, who's going to tell you more about how we got there.
Okay. Thanks, Lorenz. I was the principal investigator of the Hubble campaign that led to the discovery, and I'd like to say a few words on the history. In 2009, we ran an observational campaign with the advanced cameras for surveys on Hubble. The images to the left are from that campaign, and they show Europa in two lights within the circles, but the data were very noisy and also contained strong artifacts. Everything here to the right is an artifact, and these artifacts were also like within the data. We still try to get as much as possible out of the data, which you can see here to the right. We saw a small anomaly here, which is consistent with plumes, but it's nowhere conclusive. Next slide. Fortunately, in that same year, the space shuttle flew one last time to the Hubble Space Telescope to repair and replace some of the cameras. And the one camera which would be crucial to see plumes was then repaired by the astronauts. That's the Space Telescope Imaging Spectrograph. And once that was repaired, we went back and proposed for new observing time with Hubble with the particular aim to search for plumes on Europa. Next slide. During this first observation, we also learned about a trick how to best go about the observations. And the trick is that Europa is exposed to the harsh radiation of the Jupiter system. That generates patchiness and structure in the observations as well. This radiation is strongly controlled by Jupiter's gigantic magnetic field, and the magnetic field is fortunately time variable, which you can see here in the plot to the left. The dashed line is the magnetic equator of Jupiter, and that moves up and down past Europa with a period of roughly 10 hours. So we used that variability and designed and scheduled the campaign so that we would see the maximum variability in the data. The reason is so that we actually understand the variability and that we are able to separate the variable parts, that's the stuff that's moving, these patches that move on Europa, and can separate that from the features which are fixed on the images. Plumes sit at a certain location on Europa and therefore are fixed at a certain location. And with that trick, we were able to separate the moving parts from the stationary parts, and this was necessary to identify the plumes. Good, it's yours.
So why are scientists so excited about this result of our first glimpse of a vapor plume at the South Pole of Europa? As Jim introduced, Europa is interesting because over the last decade and a half of studies, there's more and more mounted evidence that Europa has a large ocean underneath its ice shell. The ocean's more global, as depicted on the left, in that thin blue stripe, and as you zoom into the middle image, you can see there's an ice crust on the top. And we have a lot of questions about how this works. How thick is the ice crust? Are there lakes and ponds embedded within the layers of the ice? Did these cracks go down really deep? Do they really touch that surface below, or the liquid water below the surface? We don't really know all of these things. The models that Lorenz showed earlier are really intriguing, and our data potentially helps constrain and test these models in a new way that we're really excited about. And while we don't know whether the gas we're seeing comes from too deep within the surface or even liquid water, but we have this exciting question in front of us. Does it come from liquid water below the surface? And if it does, then we have a way to explore the composition and other details of that water that's underneath the surface in a new way that wasn't accessible to us in the past. Next slide. Even if the plume isn't generated by a liquid water source, it's really fascinating. And we have two examples now in the solar system, Europa and Enceladus. And in planetary science, we like to compare different objects, and we get a deeper understanding of the physical processes involved when we do so. So let me just briefly step through a few things that we noted by doing these side-by-side comparisons. First of all, the plume density that we're looking at, as you look through the image, if you look through just a single line of sight through the plumes, the column density is really similar at both Europa and Enceladus. Europa's plume extends 200 kilometers high, where Enceladus is further out into space. Enceladus has 12 times lower gravity, so this gas escapes more readily from Enceladus than it does Europa. Next slide. The plumes vary as in intensity as the satellites move in its orbit. At apocenter, it's more intense, and recent results with Cassini show that it's about 4 times more intense at apocenter for Enceladus than at pericenter. While our results only detect a plume at apocenter, we can put upper limits on the pericenter densities and constrain that variability to a factor of 3 or more. And it's pretty similar at first glance, and so that's interesting. Next slide. Perhaps most interestingly, there are 7 tons per second of material coming out of the south polar plumes, and that's just an amazing amount. This gas is traveling more like 700 meters per second, which is faster than the gas coming out of Enceladus. But Europa's escape velocity is more like 2 kilometers per second. So all this gas is coming out, almost all of it falls back towards the surface, and it doesn't escape to space like it does to Enceladus. Next slide. We want to really emphasize that this is just one measurement, one detection with one Hubble instrument. Our understanding of Enceladus is much more refined at this time. There are tens to hundreds of different detections and measurements made with the several different Cassini instruments. And so we have a lot more to learn at Europa, and all these numbers in the Europa column are going to change in the next few years, and I think that's really exciting. Next slide. Let me just talk a little bit about future steps. As with all discoveries, you want to repeat the experiment to confirm that it exists, and so we're going to go aim to do that. Once we achieve that, we'll go and look at it with the same instrument, more instruments, and understand the composition of the plume better. We haven't seen any evidence of ice or dust in our technique that we're using right now, so that's another thing we'll be asking. And just what is the compositional, or what is the variability of the intensity of these plumes at Europa, and is it a lot like Enceladus? So Hubble's a really useful tool for this. We also have the European Space Agency has the Jupiter Icy Moons Explorer mission in the planning stages, and it will pass by Europa twice during its tour of the Jupiter system on its way to Ganymede. Now, NASA has an instrument contribution to that, an ultraviolet spectrograph, and I'm involved in that as the deputy PI. And in my poster tomorrow, I'll explain more how we're really optimistic about using this UV spectrograph to get much higher spatial resolution images of these types of auroral features than we can obtain from Earth and the Hubble Space Telescope. But let me point out that the JUICE mission is really constrained by celestial mechanics to fly by its equator on its tour to get into Ganymede orbit. And we really want to look at the South Pole and do flybys past the South Pole. Predictions show that North Pole plumes could exist. So we want to be able to have new space missions that map out the locations of these vents and cracks, and maybe even fly through the plumes, sniff them out, and then map out a trajectory for future exploration to eventually land near them, and all sorts of exciting things like that. So that's what we're talking about, and we welcome your questions.
Hi, it's Joel Achenbach with the Washington Post. Thanks for having this press conference. Can you explain, any of you, the mechanics a little bit of what seems to be happening when if it's liquid water, it hits the vacuum? Does it turn into water vapor then? Does it then split apart into atomic hydrogen and oxygen? Just give us a scenario, and please tell us, if it's not a liquid ocean that's producing these plumes, what might it be?
So as already said, we do not know yet if it's coming from liquid water directly or not. But if it is liquid water, so if these cracks kind of open at epicenter and liquid water is exposed directly to the vacuum, it just, in simple words, it just begins to boil, and water vapor is produced and ejected, like from these possibly very narrow fractures.
It doesn't freeze.
No, it's like vapor. So it's like compared to vapor here on Earth, it's rather low density vapor, but it's vapor, and is ejected like through possibly narrow fractures, so it can reach these altitudes of 200 kilometers. And then once it cannot leave the gravity field of Europa, but falls back immediately. And once it hits the surface, like it hits solid ice at minus 150 Celsius, it freezes immediately. So that's what we know. The other possible explanation that could create these plumes is like that the fractures kind of undergo parallel movements, and there's kind of a friction between these fractures, kind of rubbing your hands together. We create heat, and this heat sublimates like the solid ice directly and turns it into vapor, which is ejected here.
Liquid water cannot exist at these conditions at Europa. So the water either, like if it would come to the surface directly, because it's basically a vacuum there. So there's not a pressure like here in the atmosphere. So it would directly go into the gas phase, or it would directly feed, either one.
Mm-hmm. And while there's mounted evidence that this is what's controlling the plumes on Enceladus, there's still a lot of questions about exactly how this works beneath the surface. And so by comparing Europa and Enceladus, we really do hope to learn more.
And if I can add one thing, water, that's H2O that would come off the surface. But then it's broken apart later by the energetic electrons, by that harsh radiation that's in the Jupiter system. That breaks it up later, like when it's been vented. And this is then, we see these products of being broken apart by these energetic electrons of the Jupiter system.
That's why we call it aurora, exactly. It's much like on Earth.
Rick Lovett, freelance. I think you just answered my question indirectly. I had wondered how you had seen this and what wavelengths, and why you were seeing hydrogen and oxygen separately rather than molecular water bands of some sort.
Sorry, can you step in?
I think you're right. We didn't answer your question. I mean, the water molecules are broken up by the electrons, and in that process, you could also get a lot of OH molecules coming off, but we're only seeing really the hydrogen and the oxygen components of that breaking up of that water molecule.
Yeah, and the Space Telescope imaging spectrographs this, and the hydrogen line is the Lyman alpha line, and the oxygen lines at 1304 angstrom and 1356 we also observe, but we don't see the plume there.
So it's both far ultraviolet.
You know, relative to the environment, Galileo measured quite extensively the magnetic field of Jupiter. And of course, so what's running around the magnetic field lines that thread Europa back to the planet is a current. And so that's producing aurora on Jupiter. And in fact, Hubble Space Telescope has seen the flux tube, as we call it, of connected field lines from Europa back to Jupiter. So there's an acceleration process, there's a raining of electrons in this environment at both the north and south poles.
Maybe I can add one more thing here. So like I said, like these particles are ejected and then like reach altitudes of about 200 kilometers, fall back to the surface and freeze, and this takes about 20 minutes. And we need to like excite these emissions within these 20 minutes. So we need a process that like works promptly, and this is like these electrons hit the H2O, dissociate the H2O, and excite them at the same time. So that's the only way we can like get these emissions within 20 minutes.
Hi, I'm Irene Klotz with Discovery News. I have two questions about the implications of this research. The first is the phenomenon, I guess, strong enough to account for the planet's resurfacing? And the second one is this a possible mechanism for the exchange of surface material, possibly even organics, deposited by comets to get to the subsurface ocean? Or is this, do you not really have a sense yet of what this means to the overall Europa system and its potential habitability?
All good questions, and those are the things we're going off to answer. We were really, kind of surprised by the 7 tons per second number as we saw it, and so we're still grasping with what that means. But we really only see this at one location right now, so to try to infer that there's a global sort of effect as a result of this is a little difficult at this time.
Thanks. And the other question is it possible that Galileo would have seen this, or was that satellite or with the high band communications data issue not possible, and anybody going back to see if there's any signs of any of this in the archive data?
Indeed, the Galileo data is well available in the archive, in our Planetary Data System archive, and I believe these results will really allow researchers to go back into that archive and refine some of the analysis. It's a very harsh area, with the radiation belt. It's complicated magnetic field structures. The magnetic field instrument on Cassini was the first that indicated mass loading going on for the plumes that allowed then the imagers to go back and look and see the scattered light and see the plumes. And so now that we know where they are in terms of on Europa being observed at apocenter, the furthest location, then that narrows the window of opportunity that we have in comparison to the passes that we've made. So once again, the scientists will head back to the archive, and I think we'll have some other great results or another controversy.
Maybe one add-on to the resurfacing. It's indirect evidence that resurfacing is a very important process, because if you see plumes and they are variable, the stresses and the deformation of Europa's surface due to the tides need to be fairly strong. And if there is a subsurface ocean, that deformation is much stronger than if Europa is all the way frozen out. And so that's why we also indirectly confirm the ocean. And if there is an ocean, then also the resurfacing, that sort of the crust of Europa is turned over, is also happening much more strongly if there is this subsurface ocean, because the whole system is more dynamic. Francis Nimmo is our expert on that, so he's probably happy to add a few more words to that.
Francis, perhaps you can comment on how the ice shell actually slips over time.
Certainly. So this is Francis Nimmo at UC Santa Cruz. The most important point is that when Europa is close to Jupiter, it gets stretched and the poles get squished, and so when the poles are getting squished, all the cracks close up, and then as it moves further away from Jupiter, it becomes unsquished, the poles move outwards, and so that's when the cracks open. And so that's why you expect to see all the cracks shutting when it's close to Jupiter and then opening up, and so that's why you would predict there to be more plume activity when you're far away from Jupiter.
At the poles in particular, right?
Yeah, at the poles in particular. Mm-hmm.
Hi, we have a question from the web streaming chat. This question is from Camille Carlisle at Sky and Telescope magazine. Besides having Europa at apoapse again, what criteria are necessary for you to observe this again and confirm the result? For example, do you need to avoid reflection from other moons or hit certain times in the variability of Jupiter's magnetic field?
So basically, as Joachim said already, there's like a history of these observations, and we scheduled these observations already in a certain way. And the first thing to do will probably just to repeat the exact measurements we have here now. And there's a couple of things that is important. One is that Europa should be at epicenter again, and then we look at Europa when it's like at eastern elongation, we say it's like to the left of Jupiter when you look at Jupiter, and at eastern elongation, like the geometry, the projection effect minimize, so we have like 7 hours of observations, and we can see always the same, almost the same hemisphere, and can really separate then again what is time stationary in these images and what is moving, and yeah, that's the most important constraints on observations.
And the other part of that question I'll add is, while we do need to subtract off the reflected sunlight off of the moon, the nice thing about this discovery is that the plume is seen above the limb, and so any reflections off of the surface from the sun or other moons is something we're not too concerned about. You know, we did a careful job to account for that, but it's pretty clearly there above the limb.
I have another question from the web streaming chat. This is from Emily Lokhtawala from the Planetary Society. And her question is there any evidence for fresh snow at the surface of Europa where material from these plumes should be falling like there is for Enceladus? Enceladus, sorry.
So we do not see something like fresh snow in Galileo images, but in particular at the South Pole we do not have images with like the high resolution we would need to really see like if it's snow or if we mostly we cannot resolve this, but also yeah, with this like 7,000 kilograms per second, you would expect some kind of sign of surface changes there, but to my knowledge, has nothing in particular been detected by Galileo, and future observations will probably help there, and maybe we then find the deposits on the surface, but so far there's no signs of any.
Yeah, it's really unfortunate, as I mentioned, that Galileo had only 11 passes of Europa. That's all the knowledge that we have based and observations based from those flybys. So the South Pole is not covered very well, and I think my understanding is the highest resolution we have for some of those passes is about 100 kilometers per pixel. So it's looking for details as Emily requests would not be found in the Galileo data.
Casey Dreyer from the Planetary Society. I know that NASA's been working on this concept mission called the Europa Clipper, which would do a lot of flybys of Europa. With this new data about these plumes, would you be able to modify or kind of alter that concept to say you could fly through these plumes and sample it directly, or does this require an entire new concept? And if that's the case, how quickly could a Europa Clipper come to be if the money showed up?
Okay, so what we have been doing is studying several approaches to really understand Europa from a spacecraft in that environment, and it looks like the Clipper concept is our best one. Now that's a spacecraft that orbits Jupiter with multiple flybys of Europa, and once again we're taking a page from Cassini, for which as Cassini orbits Saturn as multiple flybys of Titan and multiple flybys of Enceladus, they're able to put together more global pictures, which is what we want. Also, based on these observations, we're going to redouble our efforts to take a good look at Clipper, its orbital trajectories, the plans for the mission architecture to ensure that we have the right instrumentation and that we can cover this area very well and really understand it. Indeed, the plumes are incredibly exciting if they are there. They're bringing up material from in the ocean. Perhaps there's organic material that will be laying on the surface of the South Pole. Those are the things that we want to know about, that we expect the Clipper mission to make major progress on. So important observations at the right time, because we're at the early stages of development of the concept of the Clipper mission. Now, the Clipper mission hasn't entered into the NASA development cycle, and that would require additional funding, which is currently not within the President's budget over the next several years. But it doesn't mean we shouldn't be looking at these and planning for an eventual Europa mission, because once again, it's one of our top scientific objects that we want to know about, and has been well represented in our planetary decadal, in the last one, but also this one, which is developed by the National Academy.
Harvey Lyford, freelance. Just a couple.
Oh, yeah, okay.
Just a couple of basic questions for you, Dr. Green. At the beginning, you said that Europa's period was about 3.5 days. Is that Jovian days or?
No, that's Earth days.
Earth days,
right?
Okay. And do you know what it is on Jupiter, or how many?
Well, Jupiter rotates in about 11 hours. That's 1 day on Jupiter. So with it, it carries its magnetic field, which sweeps by all the moons as they make their track around the planet. And so, as you saw, the magnetic equator is going to flop up and down as Europa is moving from its pericenter to its apocenter location. But indeed, it'll take 3.5 days to make that in complete circuit for Europa around Jupiter.
And the second question is, what is the actual distance at the greatest distance from Jupiter and the closest approach in this very elliptical orbit?
You guys got that handy?
I don't have the absolute numbers. Like the difference is like around 1%. Like it's 1%.
Yeah, it's not very
1%
big.
further away.
I had the impression it was much bigger.
But even that appears to have made a difference, and that's tremendously exciting.
The reason why even that little 1%, or a little bit more than 1%, makes that huge difference because Jupiter is such a massive planet.
Yeah.
So the gravitational forces of Jupiter is so much more strong than the Earth does. Like the Earth moon has a gravitational pull on the Earth, but the Earth moon is teeny tiny compared to the gravitational pull of Jupiter on Europa.
I have another question from the web streaming chat. This question is from Nancy Atkinson at Universe Today. What observation and instruments from Juno do you anticipate most for following up on this finding?
Juno is a spinning spacecraft, and it's going to fly very close to Jupiter itself, and it's not really targeted to fly past Europa. It does have some imagery capabilities, and that team is really looking hard at how we can optimize those observations. But maybe the best bet is looking for gases coming off and flowing through all the Jupiter system in terms of how the plasma in the environment interacts with that. So we really do need a really dedicated Europa mission itself.
I have another question from Camille Carlisle at Sky and Telescope. In Lorenz Roth slides, there were sketches of no fractures when no plumes, and then fractures when there were plumes in December 2012. Are those based on observations of actual fractures, or based on the exception from the squishing and stretching?
Yes, these are like, the fractures are actually there all the time, so we see these cracks on the surface, and they're all over. So in these plots, it was just like these fractures shown as dots, and when these dots were black, there was tension on the cracks, but the cracks were always there, and when these dots were white, there was compression, or at least no tension on these cracks. So they are like, it's an image of the South Polar region, and then like in this image you mark the cracks and with dots and put them like in a projection here.
From Galileo specifically, yes.
Mm-hmm. But even then, there's a significant fraction of that southern hemisphere that hasn't been imaged, maybe 40%. So you're just showing the cracks that we have been able to observe with Galileo.
Right.
Rick Lovett again. I have. You went looking for this. I kind of think I've got two related things here. I gather you went looking for a plume. What inspired you? And is there any relevance to the fact that both Enceladus and Europa are at the South Pole? Or is that just a coincidence?
To the first part, we had, because Europa is interesting for many different reasons, so that's why the 2009 campaign, we were trying to better understand the atmosphere, and we didn't really expect plumes, or that wasn't like the primary reason. But then once we analyzed these data, then we got this hint, and then by then, like the plumes on Enceladus were also like such an established thing, so that And because we had this we saw this anomaly, which we didn't expect in the 2009 data. And they were consistent with the expected location of these fractures. So, and then we really got excited. But the data were not good enough because of the artifacts with that camera. But then luckily, like with the surfacing mission of the shuttle, we had the new camera, or the repaired camera available. And then we really like went after plumes. Then it was the primary aim of the campaign, was to search for plumes. The second one, if it's on the South Pole, there's not a theory on it. It could be equally the North Pole. We don't know. There has been some theories developed at Enceladus why it is at the pole and not at the equator. And before I repeat that argument, I give it to Francis Nimmo because he had, I think, a Nature paper with Bob Pappalardo on the idea why it could be at the poles.
So there are two possibilities. One is that as these bodies get squeezed and stretched, you generate heat, and it turns out that more heat is generated at the poles than at the equator, and so perhaps the shell is thinner or something like that, and so that's why you're seeing activity at the pole rather than anywhere else. The other possibility is that, at least for Enceladus, this activity might have started somewhere else, but as the shell started to melt, that actually changed the distribution of mass within the body, within the moon, and then the whole moon tilted over until that area ended up at the South Pole. So there are two ways of explaining that.
I have another question from Emily Lochdewala at the Planetary Society. How confident are you in this detection? Are the plumes definitely there, or just pretty likely to be there? Can you quantify your confidence?
So all we can do, and we do, is that we calculate the statistics of these emissions we see, and like the hydrogen signal, as we say, is a 4 sigma detection. So there's just like a very, very small uncertainty that the signal we detect is noise or anything like in the instrument or something, and that's the way we can quantify like the certainty of this observation. And what was the second question? Sorry.
Sure. Are the plumes definitely there, or just pretty likely to be there? How confident are you?
I mean, definitely is maybe a strong word. It is just the best and only explanation for what we see and what we statistically significant detect in our images. That's all I can say.
So 4 sigma is fairly high, so we're very confident that it was there in December last year. The pattern that it goes off, that it's on at the epicenter and it closes at the pericenter, we only have 3 measurements. We have 2 measurements when it's close and 1 measurement when it's far. Then it fills the pattern, but you have only 3 measurements, and you want to establish a pattern that introduces the natural uncertainty. So there's a natural uncertainty on the pattern, but we're certain, or like within 4 sigma certain, that it was there in December 2012.
Hi, I'm Lisa Grossman from New Scientist. This might be for Francis Nimmo again, but maybe for any of you. So Europa's shell sloshes around and moves around on top of the ocean too, or at least there's been evidence for that, right? So could the plume also move around, like Enceladus, like that second model of Enceladus you mentioned? And I had another question, but I'll wait.
Yeah, I think that's perfectly possible. You would need to have you'd need to create quite a big bump for it to really shift the whole shell around, and so I tend to favor it being in place. I have just remembered, though, that there's some evidence from other spacecraft. They saw a pattern of large circles on the surface of Europa, and one way of explaining that was that the whole shell had actually shifted through 90 degrees, and so there is actually at least one other piece of evidence that Europa may indeed, the shell may have shifted by a very dramatic amount. That was work that Paul Schenk published in Nature a few years back.
It's Jonathan Amos, BBC News. Sorry if I'm in a bit late, so apologies if you've already picked this up. What you know of the JUICE payload, I'm not sure that all the instruments have been selected yet. They've only got 3 flybys from memory. What could JUICE do here to further our knowledge about this?
Yeah, the JUICE payload has been selected, and as I mentioned earlier, NASA has a U.S. contribution on that, and there are going to be 2 flybys. So I couldn't really broadly disseminate this information to the JUICE team. I just clicked send on an email this morning to all of them. We're going to go have those discussions about how to follow up. I do allude to some things in my poster tomorrow about what JUICE will do.
But what you know of what Cassini's been able to do at Enceladus, and it's been tasting the plumes there. What you know of the JUICE payload, what could it do?
Our UV spectrograph can produce really good imagery of these auroral emissions. For one thing, we're going to do stellar occultations, looking at the light attenuation as the star passes behind the plume, and that can help us understand the composition of it. And so we can do this pretty globally with these remote sensing instruments, cameras, ultraviolet spectrographs. But for the JUICE payload, there are in situ measurements where you just sort of measure particles as you fly along, or magnetic fields, and we only have observed probably one of the largest plumes on Europa, but there could be a lot of plumes, more like 10 to 50 kilometers height, and we're just not seeing them with our current data sets. So it's not improbable that the JUICE mission could be flying through and targeting some sort of plume near the equator that's just smaller, in which case we'd still have a chance to sniff out the composition of the gases coming off and do all sorts of other interesting studies like that.
I have another question from Emily. How soon could we fly Clipper there if money became available? And does this discovery warrant a reconsideration of a possible Europa orbiter?
From my perspective, of course, these observations mean that the community has a lot of thinking to do about how they can take advantage of what we're seeing. For instance, we're working towards our next discovery call. This is a potential, flyby through the plumes. That's also been discussed, flying through the plumes of Enceladus also. So those are a number of ideas for which our missions, such as those in Discovery, can take advantage of that. The Europa Clipper is a very expensive venture. It's expensive because it's designed to last for a fairly long period of time, potentially a year or several years, in a very harsh radiation environment. So consequently, that is what we would call a flagship. And right now, the budget horizon is such that we're deferring that kind of mission until later in the decade. But in the meantime, it's observations like these that will help us reformulate and improve on the Clipper concept to really be able to take advantage of understanding how the ocean may be communicating with its surface and what more we can get out of missions like that.
Okay, so I think we've run out of time. Thank you very much, panel, for your presentations, and thanks everyone else for participating. Our next press conference will be at 9, and it's on the Arctic report card.
All right. Fantastic. Congratulations, you guys.